Okay. One thing is since I'm okay, so Chandler might be able to join us later. Since I'm the academic advisor for all of you, I know some of you have talked about classes for next semester, and those of you who are GTAs have already seen emails from Sharon about like getting your classes set so she can do your tuition waiver paperwork and all of that. So if we have not carried out advising yet for spring, then let's do that. So just shoot me an email and we'll get all that squared away. Okay. Also, this time of semester has been defense season. Like the graduate school deadline for defending a thesis or dissertation for fall semester was today. So I've had 4 of my students defending their master's thesis or doctoral dissertation within the last 5 days, which not only has completely fried their brains and mine, but also has knocked me behind as far as getting your homework graded. And I see that I have homework for you for homeworks 2 and 3 that I need to do. So I've not forgotten. I have the glaring reminder whenever I go to our course homepage in Canvas. But now that all of that, now that defense season is over with, I can have some time available to get all that done. So sorry for the delay on that. Well, I imagine that I don't think anybody needs to worry about how we're doing in this class. Okay, so speaking of homework, whatever homework you currently have going, how is that going?
I'm kind of to get started. Personally, just me.
Okay. All right. We'll see. Because all right. So because I have been getting questions about 7.4 homework. So and that I think not everybody's done with that as far as I know. But okay. And so has anyone started the 7.5 stuff yet? That's the oscillatory section.
Just a
Okay, all right. So, all right. So not time for questions yet, but okay. Alrighty. So, so we have one section left when it comes to polynomial interpolation before we move on to polynomial approximation, which will be the next chapter. Okay, so also I'm trying to get some seminars lined up. There might I'm still trying to get confirmation from everybody. Our when we have seminars, we've not had any this semester. It's been a bit wacky to do anything like that lately, but normally they're held on Friday afternoons, like 2 p.m. or later. There are no classes meeting at that time. And I mentioned a talk from a current PhD student at Stanford who started his PhD at the age of 15. And I think I have him lined up for this Friday at 2 o'clock, but I'm again still getting confirmation. So Dr. Zhu is our faculty member who coordinates the seminar. So there'll be an email from him about that once we get this nailed down. And also my good friend and colleague Margot Gerritsen, also from Stanford. We're trying to get her pinned down for the probably late October, perhaps the 23rd or thereabouts. Okay. Okay. Actually, she just asked what time, because she'll be in apparently she'll be in Oregon at the time. Okay. All right. So we'll see how that goes. But I just wanted to give a heads up about that. Okay. And one other thing that's going on for more advanced students, but I wanted to plant the idea in your head for and maybe something to do for next year. A competition that the graduate school holds called 3-minute thesis. Has anyone heard of that? Or maybe got some emails about it. There's a couple of our students, Samson and Bailey, I know, are going to be participating, where you give a 3-minute discussion of whatever your research is about. So a year from now or so, if you're research active, then you should consider participating, because there's good money from this competition. I think a winner gets like $1,000 or something. It's like pretty substantial. Now, math students tend not to do well in this competition because it's for a general audience, and you give us something mathematical. As soon as you put a single equation, you're like, no. But one of our students did do pretty well last year, so there's hope. So we'll see what happens. But and this is also part of a program that the graduate school runs called PIP, Professionals in Preparation, where we have weekly meetings and various activities. So it's so that's something to think about. Like, they take applications at the end of I think at the end of spring for the following year. So it's a year-long program. So something to be aware of. Okay. All right. Now, let's see. Okay, so just all the stuff that was on my mind about things I should tell you guys about that's finally been put out there. So now I can start talking about a different kind of polynomial interpolation than what we have been dealing with. Okay, get the good old screen share going. Come on. Okay. Okay. Piecewise polynomial interpolation. But also here's the homework. This is posted in Canvas also. The explorations that I've assigned for this section, 1 through 5, with meaningless suggested due date. So instead of we're given a set of points, like before. Xi, yi. So we're still given n+1 points in the plane. Instead of finding one polynomial of degree n that will pass through all of these points, we define a function in pieces. So I just need to do a quick notation check here. I was thinking about describing something in these notes, and then when you look at the book and the notation is different. Okay. Where it has this kind of piecewise definition. So p of x is equal to some function pi of x on each subinterval. So the data all right, and I want to be clear about the points. Dang it. Okay. Now the x's, it really could have been any distinct points before, but now it's required that they are in order. Okay, and we're working with some interval AB. So A is the leftmost point, x naught. B is the rightmost point, xn. So what happens is the x values that you're given divide the interval AB into subintervals. So we have n subintervals in total. So on each subinterval, we have some definition of our piecewise polynomial for that piece. All right. All right, and we'll specify that the polynomial has some degree n sub I. Now, normally, in the cases that we'll discuss, the degree of each one of these polynomials will be the same, but that's not absolutely required. So you might have like linear on some intervals and cubic on others, something like that. However, we do define the degree is defined by I know we'll just use D to refer to it as a maximum degree of wait. Okay. Actually, I'll call this DI for a degree of each piece. So then D is a degree of a whole thing. So if you have a mixture like some piecewise linear, piecewise quadratic, or some sorry, if certain pieces are linear, certain pieces quadratic, certain pieces cubic, then the whole polynomial is considered piecewise polynomial is considered to be of degree 3. Okay. All right. So what are the advantages and disadvantages of this approach? So I really can't type today, apparently. All right, so advantages. Generally, the degree of a piecewise polynomial is low. And the benefit of that is that you're avoiding the pitfalls that happen from high degree interpolation. So I've shown an example of 1 over 1 plus x squared, where I interpolated that using equally spaced points, and the approximation, while it fit this function at those points, diverged wildly from it in between. And the high degree, as well as the equally spaced points, played a role in that disaster. But if we keep a degree low, and we just focus on one piece at a time, so we're really just approximating a function on one of these subintervals instead of the whole interval, we can keep that error low. Okay. Okay. And a drawback is well, this piecewise polynomial smooth on each subinterval, it's not necessarily smooth as a whole. So in general, you can ensure d minus 1 continuous derivatives. But for some applications, you might want to have something smoother than that, and that's something that's not going to happen. Unlike regular polynomial interpolation, on the entire interval of that contains your data, the derivatives always exist at each point. But what could happen here is, because you have all these different polynomials that are being hooked together, sure, you can make it continuous, sure, you can have continuous derivatives up to a point, but at some point, as you take derivatives of the entire function p of x, your graph will start to get kinks at it, or maybe have discontinuities, and that can pose problems in applications that require a high degree of smoothness. So that's something that's being taken away. So you're giving up smoothness to a certain extent, but you're gaining this accuracy in return. So it's a way to prevent that wild behavior that regular polynomial interpolation can exhibit, where you have a lot of oscillations in between your points. Okay. Now, I'm going to give it again, at the risk of embarrassing myself, because what I'm about to do is totally unprepared. I'm going to try to do a Matlab demonstration of piecewise polynomials. So, okay, so I need to unshare from here. Okay. And let's see. Actually, I'll need to share my desktop because just the Matlab window won't be enough. Okay. All right, now we have a demo of cubic splines. So that is a piecewise polynomial of degree 3 on each subinterval. So splines, which I'll cover in more detail on Wednesday, have nice properties of having two continuous derivatives. So it's a way to take given data and join them by, in a sense, a curve that's as smooth as possible. So I'm going to make up some data here. Well, first, I'm going to use the same function as I've used in previous examples, 1 over 1 plus x squared. The dots are in here because I want to be able to pass a vector to this function. So I'm dividing vectors or squaring vectors, and the dots will make that possible. Okay, so if I just make up some data, let's see. All right. Let's go from -2 to 2. So 5 points altogether. So -2, -1, 0, 1, and 2 are my 5 x values. My y values will just be f of x. Okay. And then I want to make it a vector of x's for plotting purposes. I'll use a lin space from -2 to 2. So for plotting graphs of functions, I'll have several equally spaced points in this interval. Okay. So first I'm going to plot the function. What? Oh, sorry. I goofed. Y should be f of xx, not x. Okay, so here's a function we're trying to interpolate, 1 over 1 plus x squared. Okay, so now what I'm going to do is use a built-in Matlab function, Spline. Okay, so my variable pp will be the output of this Matlab function Spline, and what I pass is just the x and y values that I'm trying to fit, so that describe my function. So if I just pass in my data to Spline, it returns this output pp. Now, what is pp? pp is a kind of variable that we haven't, I don't believe we have seen so far. So I'll just print it out. Okay, it's a struct. Now, depending on whatever programming experience you might have, you may have seen something like a struct before. Struct is also a term from C and C++. It is a data structure that has named fields. So I can refer to pp.form or pp.breaks to access the individual items within this structure. So form, breaks, coefs, pieces, order, div, those are the fields of pp. So if I do like pp.order, that would give me this 4 here. So the breaks are just the x values that I passed in, -2 to 2. Coefs, I print out what that is. All right. So what I have here is each row. This is a matrix, as you can see. Each row of a matrix gives me the coefficients of a polynomial. So it's so since I have 5 points, I have 4 subintervals. That's why I have 4 rows. So pp is a n by 4 matrix where n is the number of pieces. So each row describes the coefficients of a cubic polynomial for that piece. Now what I'd like to do is evaluate this piecewise polynomial to be able to show the approximation to compare with the graph of the original. Now, fortunately, Matlab provides a convenience function for that. So I can do yy2 is ppval. So this is kind of like polyval, but for piecewise polynomials instead of regular polynomials. And what I'll pass in is my piecewise polynomial, and then the x values I want to evaluate it at. So that'd be xx again. So this is a convenient way. So Spline creates a piecewise polynomial. So that's kind of like playing a role of polyfit. ppval evaluates it. So now I can go ahead and plot those values. I'll plot them in red. Oh, I goofed. Dang it. Hold on. Okay. I meant hold on in the colloquial sense, but I also mean it in the Matlab sense. I need to put the graph of polynomial back. I forgot to say hold on. Sorry, I'm off my game today. So just in general, so deal with it. But again, I'm sorry. So now I plot the piecewise polynomial. Okay. Not the best approximation, and that's because I haven't used very many pieces. It's going to agree with a function at the 5 points I selected. So I'm going to plot those also, x, y, and black circles, just so you can see it agrees at these points. And so the goal is to find a cubic polynomials for each of these 4 pieces to make sure that it has 2 continuous derivatives and fits the data. So that's the criteria here. All right. Now, now what I'm going to do is I want to show how this curve here relates to the coefficients that I showed you earlier. So these right here. So what I want to do is this is a polynomial, the cubic polynomial for the first piece that we see right here. So it's this. So I want to plot just that polynomial. Okay. So what I'm going to do is I need to extract this polynomial so I can work with it. So I'm going to call it P1. So that's pp.coefs, which is the whole matrix. But I only want the first row. So I'll just take the first row of that. And now I have these coefficients. Now, what I'm going to do is use polyval. This is a regular polynomial, a cubic. So the y values for the first piece would be polyval of this polynomial evaluated at xx, which is my points for plotting. Now, what I'd like to do is plot that too. Sorry. I want to plot it in green to distinguish from everything else. Actually, use magenta. That might be easier for you to see. Okay. Here it is. And as you can see, it seems to have no relation whatsoever to the piecewise polynomial over here. And the reason why is because I intentionally screwed up. And I'm not joking. I intentionally screwed up because this polynomial here, normally polynomials are described in Matlab as in power form. So it's minus 0.3x cubed plus x squared minus 0.4x plus 0.2. But these polynomials are actually in shifted form. So each polynomial piece, so row I of the coefficient matrix is in shifted power form. So what does that mean? It's a polynomial of this expression, not just x to a power, but x minus xi minus 1. So it's really minus 0.3 x minus 2. Why minus 2? Because that's the x value at the left of this piece. A polynomial not of x, but of x plus 2. So what I'm going to do here is I need to delete this curve because it's wrong anyway. Come on. Okay. So now I'm going to try again. So for my x values, I want this to be a function of x minus a minus 2. So x plus 2. Whoops. Not that command. I need this command. Okay. Okay. So now I'll plot again. Okay. I'm going to try. I need to zoom in a bit here. Okay, so this is the same view we had before. Now, here for red, that's a piecewise polynomial for the entire interval minus 2 to 2. Here is, in magenta, is a polynomial just for first piece, and I've graphed it and let the graph keep going. So here it agrees with a piecewise polynomial because this is a polynomial that was used for a first piece. So here it should coincide. And then eventually it deviates because it's only meant to be used for this piece. It's kind of surprising that it happens to agree with this one too. That's just a freakish coincidence, though. So this is something to keep in mind if you want to look at the individual pieces. So really, these 4 cubic polynomials are pasted together or hooked together to ensure that we get a nice smooth curve that approximates the underlying function, in this case, 1 over 1 plus x squared. All right. Sorry, what?
Do you mind explaining the shift one more time?
Okay. So I need to think of, so actually, I'm going to look at 2 things here. Here are the coefficients, and then pp dot breaks. These are just the x values that were passed. So for this first piece, we need to think of it not as a polynomial of x, but a polynomial of x minus this value. So these coefficients are with respect to, it's using this as the origin. And then this one using this as the origin, and so on. So to be able to see what the polynomial actually is, what you would do is you would evaluate it not at x, but x minus whichever one of these it is.
That makes more sense. Thank you.
And to show you what this looks like just in regular math notation, okay. And you'll see this when we get to more to cubic splines. Each piece is described this way in this shifted form. So AI, BI, CI, DI are the coefficients in increasing degree. And notice that we have x minus the left endpoint of a subinterval raised to powers. So this is a representation that's used in Matlab also. And this form makes it more convenient for coming up with all the conditions that these coefficients have to satisfy to make sure it fits the data, to make sure it's continuous, and so on. All right. Now, are any other questions about the Matlab demo?
On PP, all those functions that it has, does that also happen for XX and YY, or is that only because it's P's?
Okay, I'm sorry, for you repeat again?
How PP, you said, is a struct, so it had all those extra aspects of it. Does that also happen for the XX and the YY, or is it only because it's a P?
Oh, okay. So in other words, it's just being a structure and having those properties. I'm not.
How did you make it a struct? Is it just because it's P, or is it because you doubled the letters?
Okay. Oh, I see. All right. Sorry, it took a while to get at the heart of your question. Okay. No, I did not make it a struct. That function, Matlab's function Spline, made it a structure.
Okay.
Yeah, the doubling of letters, that's like, PP stands for piecewise polynomial. That's why I called it that. And actually, I wonder if we can look at the code for Spline. Because some functions it says it's built in, but okay, actually, this is a code for Spline, although it's calling certain other functions. Oh, Okay, yes, there's other functions that do all the dirty work. We might not be able to look at those. Let's see. Okay, it's a very various function mkpp. Okay. Oh, make piecewise polynomial. So here, if given the breaks and the coefficients, this is what actually creates the structure. So I want to see if I can find an example of what it's doing. Let's see if we can look at that code. Oh, we can. Oh, yeah, here it's filling in all the different things. So it comes up with the values to put in the struct, and here it's creating the actual structure. So that's something that you can do with any variable that you're working with in Matlab. You can take a variable and make it a structure, but then once you do, that's what it is. And I mean, it follows the same rules of any other variables in Matlab. Once you assign it to something else, then it's overwritten. So then you can use these expressions as in other expressions. Other questions about the Matlab stuff? I should point out another way of using spline. This is if you don't really care about the structure of the coefficients. I could do this, like yy equals spline. I'll call it something else, yy2. So you pass the data like before, and then if you just wanted to evaluate the spline at certain x values, I can do this. So here you don't get a piecewise polynomial structure like before, because this interface Spline is only for evaluation. So and ppval in one step. But now you don't have the PP structure if you wanted to look at that later. So if you don't care about the particulars of the structure, like if you have no need to examine the coefficients, then you might just want to go ahead and do this. And then you get, if you just want the values that select points in the interval, then that'll take care of it. But if you if you are not sure where you want to evaluate the piecewise polynomial, you might want to evaluate it at many different x's. But you probably want to use the first form where you get the piecewise polynomial structure output, and then you can use ppval to evaluate it after that. Okay. Now, during the rest of the day, I'm going to focus on cubic splines on Wednesday, because those will take more time. But I want to take a look at a simpler form of piecewise polynomial. Of the simplest form of all, piecewise linear interpolation. So the idea is so piecewise linear polynomial that fits the x's and y's that you're given. It's given by the following. So each piecewise polynomial, pi of x, is defined to be y I minus 1 times x minus xi over xi minus 1 minus xi, and plus yi, a similar fraction, okay, and that's for each piece. All right, so if I plug in, okay, I actually need to define a domain for this. Okay, so if I plug in either one of these x values into here, I will get the corresponding y value. And that's something that you can check directly. Otherwise, this piecewise polynomial is only valid on this interval. So it's only meant for that piece. Now, the simplest way to describe this piecewise linear polynomial is connect the dots. So if you were to plot all of your points, all n plus 1 of them, in the plane, then the polynomial, the function you get by simply connecting the dots by straight lines going from left to right would give you exactly this function. So that's the graph of it. Is continuous because you are drawing a line, because you are connecting the dots. But its derivative is not continuous. So its first derivative is only piecewise continuous. So for applications where you need a smooth approximating polynomial, this is not helpful. But there are many applications where piecewise linear functions are used, for example, for solving certain methods of solving differential equations, like finite element methods, rely heavily on piecewise. So they do have their use. Okay. Now, I want to talk about error. So we know what the error in polynomial interpolation is, regular polynomial interpolation. But what about piecewise polynomial? It's actually the same thing. But this interpolation error formula is applied on a piece-by-piece basis. So p of x is the piecewise polynomial interpolant of any degree, not just piecewise linear. Okay. Actually, sorry, I do need to specialize this to the linear case. So piecewise linear interpolant. Okay. For the given data, xi, yi, then here's the error. Well, okay. Because we're assuming that we're approximating a certain function, f of x. So this polynomial will match this data, but how closely does it approximate f in between? So f minus the piecewise linear interpolant. Okay. I actually want to check something here. By piecewise linear section. Okay. Okay, so this is, and it's called linear spline, but it's a piecewise linear interpolant also. Okay. Okay. Well, let me make a note of that here. Okay. Okay. All right, so here we have a piecewise linear spline. Then on each piece, each subinterval, then the regular formula for polynomial interpolation applies, for a polynomial interpolation error. Because this is a polynomial interpolant, an ordinary polynomial interpolant that fits f of x at these 2 points. So those are the interpolation points for that piece. So on this piece, and only this piece, this is where we get to the error in like Lagrange interpolation. That formula still applies. So there's actually a theorem in the book that comes up with an error bound from this formula. And one of the homework problems is to prove that theorem using this as a starting point. And that theorem is this right here. So actually, I do want to talk about that briefly. So I want to talk about the notation. So we could say that's f minus s So on the interval AB, which is the interval defined by your data, remember A is x naught, B is xn. Then we have the error satisfying this bound, where H is the maximum of a maximum spacing between the x values. Okay. And what does this symbol mean? This is the infinity norm of a given function. So it is the maximum. In this case, we're considering the interval AB. So it's the maximum of the absolute value of f on this interval. And m is the maximum, therefore the infinity norm, of f double prime, which we see is involved in this formula here. So one of the homework problems is to use this to infer this. Okay. So we see that the error is proportional to h squared, the maximum spacing between points. So as you're using more and more points to fit your piecewise interpolant, the error would be going to 0. So in other words, the maximum possible error rate you can get. Assuming that the function has 2 continuous derivatives at least. All right. Sorry, couldn't resist. Questions about what we have here? Theorem 7.4.1 is the error formula for Lagrange interpolation. All right. Now, so that's one nice thing about piecewise polynomial interpolation compared to regular polynomial interpolation. At least as you use more points, you can confidently say that the error is going to go to 0. Whereas with regular polynomial interpolation, because the polynomial can behave very wildly between these x values, you can't be sure of this kind of behavior. As you use more points, the error might not be going to 0. So Runge's example is illustrates that. Okay. Now, the last thing I want to talk about for piecewise linear interpolation is so another property that they have is piecewise linear spline is the flattest function that fits the given data. Now, what does that mean? That I'll explain all this notation in a second. All right, so I'm still using the letter S to refer to the piecewise linear spline, the connected dots function. So its derivative satisfies this condition where V is, I want to get my notation straight again. Okay. All right. All right, so I need to describe for you what this is. This is a function space defined on the interval AB, and I need to explain to you what that is. And that's something that's buried deep in the appendices. Okay. Okay. H1AB is an example. It's called a Sobolev space. So H1 of AB is a set of all absolutely continuous functions whose derivatives belong to L2. Now I need to describe this function space also because that's something I need for what I'm doing here. Now, All right, so L2 of AB let's satisfy this condition. Because this 2 norm, I needed to define that anyway. So I need to be able to integrate the square of f on the interval AB and have that be finite. So L2AB is a set of all functions that satisfy this condition. In other words, the functions are square integrable. It certainly includes continuous functions on AB, but other functions as well. Like for instance, piecewise continuous functions would work. Okay, that should be a X, not an S. All right, so functions whose derivatives satisfy this condition belong to H1. So of all functions that have square integral first derivatives and are absolutely continuous, that also sorry, I need to make clear here. Okay. Not just any function in this space has to fit the same data and is in this space. Okay. So I could define all kinds of functions that pass through the same points, but maybe they behave wildly in between. But this one doesn't. I mean, it's just connecting the dots. But it can be proven that this function has the least wild behavior of all functions that pass through the same points. And in the book, the proof of that is started. Okay. So what I can do is the following. I can write S prime, the square of its 2 norm. So this 2 norm is a measure of magnitude of functions on AB. So I'm trying to show that S prime has less magnitude in this sense than B prime. So what I can do to prove that is I can write it as S prime minus V plus V. Okay. And if I group S prime and V together, actually want to make sure that I'm setting this up correctly. Oh, yep, I knew it. I had to do it the other way around. V prime. Okay. All right. Now, I can use, I can actually break up this sum in a sense. So this is equal to S prime plus 2 times, what's called the inner product of S prime with this function here, V prime minus S prime, plus that. Where so I need to define this notation. It's called an inner product of real value functions in AB. I had to say real valued because if I do not have this qualifier, I have to take a complex conjugate of it. So then I can say that the 2 norm of F is equal to the inner product of F with itself and taking the square root. Okay. Now, so one point I want to make in general is if you have some inner product, any valid inner product of vectors, like this one here, where the vectors in this case are functions. With induced norm, because if you have a valid inner product, then the inner product naturally induces a norm by taking the inner product with itself and taking a square root. Then this is something that always holds. That's the norm of a sum or difference squared is equal to norm of F squared minus, in this case, because I have a minus here, 2 times the inner product of the 2 items being subtracted plus the norm of G squared. So you can always break it down like that. Anytime you have now, in way back in calculus, you dealt with dot products of vectors in n-dimensional space, and the magnitude that's associated with that just comes from a distance formula. So this kind of relationship applied there. You might have used that in calculus, but anytime you have some form of inner product or dot product that has this natural notion of a magnitude that goes with it, you can do this. So that's what I've done here. I've taken V prime and written it this way. Okay. So how does the proof proceed? Homework problem that this part here is 0 because of S being a piecewise linear function. That's very important. So if you show that this is 0, then the norm of V prime squared is the norm of S prime squared plus this, which is something positive, or at least non-negative. Therefore, this has to be greater than or equal to this. It's all because you know that this is 0. That's the key. Because the norm of anything has to be non-negative. It's one of the conditions to be thought of as a notion of magnitude for anything. That's how a lot of proofs go when you're trying to prove some kind of bound like this. That if you're trying to show that this is less than or equal to this, then you show that this is equal to this plus something that has to be non-negative, and that would establish it. So this is an example of a proof like that. So in some classes where you may have to do proofs later or dealing with that now, that's the sort of thing that may very well come up. I realize that I've dumped a lot of notation on you just today. And it's actually the inner products and norms are extremely important concepts in numerical analysis and other areas of math. And we're going to see more of this when we get into the next chapter. But that's why I wanted to relate it to something that you definitely would have seen before, dot products and magnitudes of vectors, where all of the same principles are at play. We're just applying those same ideas of inner products and notions of magnitude that come with them to functions instead of vectors in Rn like you would have seen before. Okay, but now that I'm through dumping stuff on you, does anyone have any questions about what happened here? Or did I fry everyone's brain to a crisp? Sorry if I did. Actually, let's flip back to Matlab real quick. Okay, so if I delete the magenta curve here. All right, so we're left with the original function in blue, the piecewise cubic function in red. So now if I plot the original x and y values, oh, I need to do it in a different color. So I want to delete that. Oh, I hope I don't delete the wrong thing. Okay, good. All right, let's plot that in black. Okay. And actually, I think I'll make that a little thicker. Okay. Actually, I'll make the rest of them thicker also. Maybe not that thick. Okay. Hello? Okay. Okay. So if we look at the black here, between any two of the points, like here we compare black for blue versus for red. So all of these functions are in H1 of AB. That means they have derivatives that are at least piecewise continuous. Now, and we see here that the black one is definitely the flattest function. It's certainly flatter than the other two that are being compared against. But since it's a straight line, well, you obviously can't get any flatter than that. So intuitively, it makes sense that if I'm looking at all functions that pass through these 5 points, that the one that's a straight line between them would indeed be the flattest. But it's nice to have this mathematical notion of flatness, that you're looking at the magnitude of a derivative and showing that that is as small as possible. So that's what the piecewise linear spline satisfies. Okay. I just realized that since I'm showing my desktop, now I guess on my screen you're just seeing you guys, right? Okay, sorry about that. I'll try not to do that too often, but I try to check in just to see, just to check facial expressions in case you can actually smoke coming out of anyone's ears. So, all right, because that's something I worry about now and then. Okay, so good luck with whatever homework you're doing, and of course you have a while to do the new ones I've done here, which actually will be mostly on the piecewise linear case. If I look at the problems I'm given, yeah, I gave you problems 1 through 5, so 1 through 4 already cover this, and this fourth one actually is simpler than all the definitions I've given you today might suggest. So there'll be one more problem that'll be on cubic splines, and that's what I'll cover on Wednesday. Okay. So as I mentioned at the beginning of class, if I've not advised you for next semester, let's take care of that sooner rather than later, because it'll be around this time when students can start signing up for graduate classes or any classes. Not that graduate classes fill up, obviously, but still. Okay, so I will see you all on Wednesday.